My name is Reuben Covey, and I'll be discussing my findings from the Lab5 Choose Your Own Adventure. In this lab, we were given the freedom to choose to experiment and model any system of our choosing. We chose to model the well-known phenomena of how two objects of different masses will still fall at the same speed and reach the ground at the same time. We chose to model this from two separate angles and formulas, which we can use to prove why this would hold true mathematically. We can see this through the lens of both Newton's second law and the energy principle, which we will go into further later on. After completing both the experimental and computational portions, we found that both the predictions and real results all hit the ground at the same time. The two most important physics principles used were Newton's second law and the energy principle. Newton's second law states F equals ma, which then can be used to derive numerous other important formulas such as the velocity update formula and the position update formula. We also use the energy principle, which states that for a falling object, the change in kinetic energy is equal to the change in potential energy. Additionally, the total change in energy of the system as a whole will be equal to zero. For a physical experiment, we studied two systems, a mass of 20 grams and a mass of 100 grams. To perform this experiment, we held both masses at the same height relative to the ground, a distance of 1.2 meters, and let them begin their free fall at the same time. We uploaded the video to the tracker software and used it to obtain position versus time data of both masses as they fell. For our computational model, we first had to set initial conditions to match that of our experiment. To do this, we created two masses with the same mass as the two real-world objects. We also set the two objects' initial positions to be the origin and their initial velocity to be 0. An additional g constant is set to be 9.8, which is the acceleration at Earth's surface. We also initialized the kinetic energies of both objects to be 0 and their potential energies to be the result of mgh, where h is their distance off the ground of 1.2 meters. The main computational loop starts by calculating the force of gravity acting on each mass. We then store the kinetic and potential energies in a variable for use later on. We can use these values as well as the calculation of the new respective energies to calculate the change in total energy of the system as well as the change in each individual energy type. Next, we use Newton's second law and the velocity and position update formulas to update the masses, positions, and velocities and display this on the model. We finally increment our time by delta t in order to continue moving towards the end of the loop. As we can see from the graphs to the right, our computational model predicted both the 20 gram and 100 gram masses to accelerate at the same rate, resulting in equal velocities and equal position data over time for both as well. Additionally, we can see from the graph on the left, where all four sets of results, both computational and experimental data, are combined into one graph where we can clearly see the overlay of each mass having the exact same position over time. With the table data showed on the right, we can further see that each mass stays at the same relative position over time as one another. Additionally, we can see in the energy graphs on the bottom that both masses increase in kinetic energy at the same rate, decrease in potential energy at the same rate, and both have a total net change in energy of 0 at all times throughout the experiment. The reasoning for why this is true, that two masses of different masses fall and reach the ground at the same time, can be seen in the mathematical formulas that relate to these concepts. Through the lens of Newton's second law, F equals m times a, force at hand is gravity, which is equal to m times g. In this sense, mg equals ma, so the masses will cancel out and not matter, resulting in a constant acceleration of 9.8 meters per second squared. This additionally holds true for the velocity update formula, where one force is divided by mass. The two masses will cancel out, resulting in the velocities of both masses remaining the same throughout. Through the lens of the energy principle, we know that the change in kinetic energy is equal to the change in gravitational potential energy, so the masses will once again cancel out, and therefore the final velocity will not rely on the mass of the falling object. Although our data overall was very accurate and reflected very consistent results, there were slight deviations in the experimental data, which can be seen as small bumps in the overlap position curve graph. The most likely cause of this error is from human error during the production of the experiment. This comes in two forms, one from a slight angle of camera recording, which causes the vertical y-axis to not perfectly align with the motion of the falling objects. The second source of error is from the dropping motion, where each mass might have been released at slightly different times and velocities, resulting in small differences in the data. But what if the objects were of different shapes instead? Although we have learned that mass will not affect the speed at which objects fall, this does not mean that our results will hold up as nicely when differing shapes are taken into account. The force of drag is an upwards force that will slow down the descent of falling objects in the real world, which is difficult to model in a computer simulation. The strength of the drag force depends on the mass of the object. To visualize this, think about how a large metal rectangle will reach the ground much faster than a thin piece of paper that is strongly affected by the drag force opposing its descent, even though the two are the same shape.